On a mountaintop at the western edge of the Sahara, where it has not rained in years, a wall of mesh is producing drinking water out of thin air. Not with pumps, not with electricity, not with a single drop of fuel. Just fog, gravity, and a net designed so that a 120 km/h storm passes straight through it. On a good foggy day, it yields about 22 liters of clean water per square meter, and it supplies 16 villages that trucks used to reach once a week. And the strange part is not that it works. It is that this exact idea was declared dead once in Chile. It was first solved 1,000 years ago by a tree, and it still carries one problem its own engineers have not cracked. Start with the counterintuitive part. In a coastal desert, the water is not in the ground. It is in the air, moving past in the fog. A dense ocean fog can carry more usable water than the dry aquifer beneath it. The problem was never whether you could catch it. The problem was that the first people who tried caught 15,000 liters a day and then watched a single storm tear the whole system to pieces. This is a story with 5 pieces. A catastrophic failure in Chile that made experts declare the whole idea dead. A German designer who figured out the one thing everyone got wrong. A medieval tree and a pre-Inca cistern that turned out to hold the blueprint. A pipeline built by hand with no power at all. And a self-cleaning trick copied straight off a cactus, plus a question about the fog itself that nobody has fully answered. 5 pieces. It begins with the failure everyone remembers as the end of fog collection. Start on a mountain in Chile. The Atacama Desert on the coast of Chile is one of the driest places on Earth. Parts of it have gone decades without measurable rain. In the late 1980s, the small fishing village of Chungungo ran out of water entirely. The local wells had dried up. Water arrived once a week by truck, and people stood in line for hours to buy a limited ration. A group of researchers tried something that sounded absurd. They climbed the neighboring mountain El Tofo and installed large, flat vertical nets of plastic mesh. The goal was simple. The Atacama coast is swept by a dense ocean fog the locals call the Camanchaca, and the nets were there to catch it. As the fog drifted through the mesh, microscopic droplets stuck to the fibers, merged, grew heavy, and ran down into a channel. It worked far better than anyone expected. The system began collecting up to 15,000 liters of drinking water a day. For the first time, the people of Chungungo could plant gardens around their houses. A village that had been rationing trucked water was suddenly, quietly, water secure from fog on a mountain with no energy at all. Saracita at the Catholic University of Chile. Fog collection is not making water, it is intercepting water already moving past. And then the desert took it back. One day, a storm rolled in off the ocean at more than 100 kilometers per hour. The flat nets did the worst possible thing. They caught the wind like sails. The rigid metal frames bent under the pressure. The steel support cables snapped. The plastic mesh shredded in minutes, and every liter of collected fog drained through the broken channels straight into dry sand. That single failure did more than wreck one village's supply. Investors pulled funding from similar projects worldwide. Most specialists in the field officially concluded that fog condensate collection had no future, that you simply could not harvest water from the air at industrial scale. The idea was, for practical purposes, declared dead. Fog is not weather. In a coastal desert, fog is the water table, floating. The Chungungo nets proved you could tap it. Then they proved that tapping it was the easy part, and surviving the wind was the hard one. The problem sat unsolved for years, until a German designer looked at the wreckage and saw the one mistake everyone else had missed. Years after Chungungo, a German industrial designer named Peter Trautwein went back to the wreckage on paper. He studied the Chilean structures in detail, the bent frames, the snapped cables, the torn mesh, and he found the mistake underneath all of them. Everyone had been trying to build a fog net strong enough to resist a storm. Trautwein realized that was the error itself. The force of a storm cannot be beaten by rigid strength. A flat net is a wall, and a wall in a 100-kilometer wind becomes a sail that rips its own supports out of the ground. The answer was not a stronger net. It was a net that stopped fighting. The structure had to move, and the wind had to pass through it. There is a familiar version of this idea. Think of a sailboat in a strong gust. You do not lock the sail rigid and hope it holds. You ease it, You let some of the wind spill through, and the boat survives the gust instead of capsizing in it. Troutwine wanted a fog net that behaved the same way, a surface that spills the storm and keeps the water. He founded a company called Aqualonis and spent years in wind tunnels in Munich, testing materials and geometries. The result was a system they named CloudFisher. Instead of a flat sheet, it is a three-dimensional mesh woven from a tough, single-strand monofiber. The geometry of the weave lets hurricane-force wind pass through the fabric without building up aerodynamic pressure, while the three-dimensional cells still trap the microscopic droplets the fog is carrying. Troutwine, founder of Aqualonis. The flat nets fought the wind. CloudFisher lets the storm pass through. To prove it, they chose the harshest test they could find. The team packed the mesh and traveled to the western edge of the Sahara, to the summit of Mount Bout Mesgida in Morocco, at about 1,200 meters. The local population was skeptical of foreign engineers, promising water in a place where it had not rained in years. On that summit, the wind hits 120 kilometers per hour. The storm hit the mesh, and the mesh did not move. The wind poured through it. And in the cells left behind, millions of microscopic droplets of fog began to collect, grow heavy, and run down the vertical channels. At 1,200 meters, on a mountain the experts had written off, the engineers collected their first drinking water. The Chilean nets failed because they fought the wind. CloudFisher works because it lets the wind through. But Troutwine did not actually invent that idea. He found it. And the place he found it had been sitting in the historical record for 500 years. Go back to the 15th century, to the island of El Hierro in the Canaries. When Spanish conquistadors landed, they found no rivers and no lakes anywhere on the island. By every rule they knew, the place should have been uninhabitable. And yet the indigenous Bimbache people living there had never suffered from a lack of water. They had a source, and they hid it. The source was a tree. The Bimbache called it the Garot, and they camouflaged the paths that led to it so no invader could take it. When the Spanish finally found it, they thought they were looking at a miracle. Beneath the tree's dense canopy sat rock basins that stayed full of clean water constantly in a place with no rain. It supplied the local people and eventually the Spanish garrison until a powerful storm destroyed the tree in 1610. It took 3 more centuries for scientists to explain it. The Garot did not produce water. It was a natural fog collector. El Hierro sits directly in the path of humid Atlantic trade winds, and the tree's broad laurel leaves captured the finest particles of vapor from the clouds drifting through. The condensed water ran down the leaves and the trunk into the basins below. A tree had been running a fog harvesting operation for centuries before anyone understood what it was. And this is exactly what Troutwine reverse engineered. He took that natural model, the physics of how a dense canopy distributes and captures droplets, and translated it into a matrix of engineered fiber. The crude plastic sheet of the 20th century experiments was replaced by a structure that reproduces on purpose what the Garot tree did by accident. The tree was not even the oldest example. In the Moquegua Valley in southern Peru, archaeologists found a network of stone reservoirs on the tops of the hills. There were never any rivers up there, and the groundwater sits more than 100 meters down. The channels were laid out along the cliffs, running perpendicular to the direction the ocean clouds move. Sediment in the bottom of the collectors was dated to around the year 1001. Centuries before the Inca, a pre-Inca culture built a large-scale system, by hand, to harvest water out of the air. They planted dense trees on the passes where wind sped up, or built barriers of reeds, caught the vapor in the branches, and channeled the condensate down into covered stone cisterns that kept it from evaporating in the daytime heat. It watered entire settlements and irrigated farm terraces in the middle of a desert. The engineering is new. The idea is 1,000 years old, and it grew on a tree. But knowing how to catch the water on a summit was only half the problem. Getting it down to the people who needed it, with no power and no roads, nearly killed the whole project. Here was the new problem. The water was now sitting on top of an isolated summit, and the people who needed it were not. 16 Berber villages were scattered down the mountain between the source and their homes. Between them stood steep rock walls with no roads and no power lines. You could not run an electric pump up there. And the families below were still spending 4 hours a day searching the plains for dirty water. There was a human obstacle too. For years, local merchants had sold water into these villages at enormous margins. A free, permanent water supply was a direct threat to that business, and some of them opposed the new infrastructure openly. The engineers had to move thousands of liters down the mountain using not 1 kilowatt of energy, or the whole installation would just stand there as an expensive monument. The solution was more than 10 kilometers of pipeline laid through the rock by hand. Heavy construction machinery could not reach the steep slopes of the Mount Mesquita range, so workers broke the hard rock with picks and levers in 40-degree heat. Every single length of pipe was carried up the mountain on people's shoulders. It took months of continuous physical labor, and it connected the high-altitude collectors to all 16 settlements at the foot of the range. And then the physics took over and ran the system for free. There was roughly a 500-meter drop from the summit to the houses. That altitude difference is a pump that never needs fuel. The water flows down on its own, and the natural slope holds a stable pressure of about 5 bars all the way to the most remote homes. No generators, no electricity bill. The pipes were buried more than a meter deep to protect them from the scorching sun. Buy roll at the IEA. Most water technology comes with a megawatt hour. This one does not. Then came the part that actually made it last. The Darcy Schmad Foundation handed the running of the distribution nodes to the local women. In these villages, water had always been women's work and women's time. The engineers taught them to monitor line pressure and to report leaks by text message through autonomous sensors placed across the network that feed data straight to their phones. That ended water theft, and it let the community fix faults without waiting on European specialists. The impact landed fast. Before the system, women were spending 5 hours a day hauling heavy jugs from polluted plains. After their homes were connected, that changed within 30 days. The time those women got back went from 0 to 95%. Families started growing vegetables in small plots right beside their houses. Bargak of Darcy Schmad. The mesh harvests the water. The women who run the network return the time. The system worked. And then the Sahara sent the one thing that could shut it all down in minutes. Then satellite radar picked up a massive dust cloud forming deep in the desert. A sandstorm winds over 25 meters per second, lifting dust 2 kilometers into the air, moving straight toward Mount Mesquita. And the engineers knew exactly what would happen if that dust met the morning fog. Dust plus fog does not make water. It makes liquid mud, and mud clogs the mesh into a solid crust that bakes hard in the heat. The storm hit. Visibility on the summit went to 0. The pressure gauges on the pipeline dropped in minutes, and drinking water to all 16 villages simply stopped. The mesh was caked in a thick, drying layer of clay, and the system lost its ability to catch moisture at all. Without an immediate fix, a high-cost installation was hours away from becoming a useless wall of clogged fabric. The answer, again, came from the Atacama. In the driest place on the planet, where there has been no rain for decades, biologists had found isolated patches of green fog oases, kept alive by nothing but the ocean fog. The scientists studied how the local cacti survive in a world made of dust. The cactus uses passive self-cleaning. Its surface is covered in microscopic cones, and desert dust cannot get a firm grip on them. When the first drops of fog condense on the tips of the spines, they grow heavy and run down the plant, and on the way they act as a cleaner. The running water sweeps the accumulated dust down to the soil and instantly frees the plant's surface to absorb clean moisture. The German engineers copied that algorithm into CloudFisher. They set the structures at a calculated angle and gave the polymer fibers an ultra-smooth coating so dust cannot bond to them either. Now, when a dust storm passes, the system runs itself. The first 15 minutes of the morning fog are spent washing the nets. That first flush of dirty water drains to the soil through a separate channel, and the moment the fibers are clean, pure drinking water starts flowing into the tanks again. In 2016, at the United Nations Climate Conference in Marrakech, the Moroccan project won the Momentum for Change Award, recognized as a benchmark for climate adaptation. From there, CloudFisher scaled out. Installations went up in Yemen, Oman, South Africa, Chile, the Indian state of Gujarat, Colombia, and Jordan. In Gujarat, the nets became the main water supply for rural settlements during the gaps in the monsoon. Aqualonis. No electricity, no fuel, no chemicals, and a cost per liter that sits below desalination. But the story does not end clean, and it would be dishonest to pretend it does. There are 2 hard problems the technology has not solved. The first is climate change. Satellites have picked up a shift in the cold ocean currents that feed these fogs, and in key collection regions, the morning humidity is thinning. Annual measurements show the amount of vapor in the air dropping by around 3% a year, which slowly starves the nets of the very thing they harvest. This is the honest counter. The fog we harvest is the fog desert plants and animals live on. Scale is the open question. A cactus solved the dust problem a million years before the engineers did, but the fog that fills a family's tank is the same fog a desert plant was counting on, which leaves a strange and quiet conclusion about where fresh water actually comes from. A technology that Chile's failure had declared dead. A German designer who realized you win against a storm by letting it pass through you. A medieval tree, and a 1,000-year-old cistern that held the blueprint. 10 kilometers of pipe carried up a mountain by hand, run by 500 meters of gravity, and a network of women with phones. A self-cleaning trick copied off a cactus, and a per-liter cost that sits below desalination in a machine with no moving parts to speak of. 5 pieces. None of them on their own was enough. The catch, the redesign, the ancient blueprint, the distribution, and the biomimicry that keeps it running through the dust. Together, they turned fog into a stable water supply in a place that had given up on rain. No electricity, no fuel, no chemicals. The only running cost is replacing the net, one thing to sit with. The same climate change that makes water scarce down here is also thinning the fog up there, and the fog these nets harvest is the fog the desert ecosystems were already living on. At today's scale, that trade-off is tiny. The interesting question is what it becomes if this spreads to every foggy coast on Earth. So, here is the real debate. Is passive fog harvesting a genuine answer for the world's dry coasts, or is it borrowing water from ecosystems that cannot spare it? Drop your case in the comments. I would rather see the trade-off than the slogan. People looked down for water for centuries. The whole time, it was moving past them in the air. That is the pattern. It was never about making water. It was about catching what was already there,